Greetings, math friends. I'm going to look at a geometric proof, and we're going to do this proof in plane geometry, Euclidean geometry, the type of geometry that you would normally learn in high school. This is a modification of something that I saw posted in the comment section of somebody else's channel, and I took a look at what was asked to be proven, and I put together a proof, and then I realized I hadn't used one of the givens, and that given was really important because depending on if you use that given or not, or paid attention to the repercussion of that given, it changes your outcome. So I have this stated so that it is provable, and then I want to look at what happens if you change something and then see how the proof falls apart. So we're going to start out with being given a triangle. The one angle is going to be defined as acute, and then we're going to have some perpendiculars come in here. And what this is doing is it's creating altitudes at the triangle. And so we're going to have ZA is going to be perpendicular to XY. XY is already in the triangle, so we're going to create the segment ZA through here, and that's going to be one of the altitudes for the triangle. So as we look at this altitude in here, this is going to be segment ZA, and then we also need to add in YB perpendicular to XZ. So we're going to come across here and create another altitude for this triangle. Looking at the triangle XBY, I'm going to just draw this off to the side. We know that this is a right triangle because we have this 90-degree angle here. And I also want to look at the triangle of XAZ. Now, XAZ is also a right triangle. If my diagrams don't look quite like right triangles, don't believe the diagram, believe the mathematics, believe the labeling that we give it. So I have these two triangles here. And now I'm going to put a little right up to this. So we're going to focus on these two triangles. So observe that triangle XBY is similar to triangle XAZ. Now, how are we going to make this claim? What we have is we have X and B are congruent to X and A in the two triangles. So we have angle X is congruent to angle X. It's because it's the same angle. If you want to give a reason, it's the reflexive property. And then B and A are congruent. And that's because they're both 90-degree angle. All right, so since I have two corresponding congruent angles in two different triangles, that means that the third angles have to be congruent. That means that angle Y and angle Z have to be congruent to each other, and that's by the third angles theorem. All right, so now we have that these two triangles are similar. Not that the two triangles are congruent to each other, we're just establishing that they're similar. Right triangles with corresponding congruent angles, so they're similar. And it also follows from the definition of similar triangles that these sides will be proportional to each other, so we can establish some proportionality. So I have xb divided by xa will be equal to by divided by az, and that's going to be equal to xy divided by xz. All right, so we have that proportionality. And now we're just going to focus on two of these ratios. We're trying to prove something about xy, xa, xz, and xb. So I have xb and xa here. I have xy and xz here. So I don't really need the center ratio. So we're just going to drop that ratio and look at this. So we just have a pair of ratios that are equal to each other. So this is equal proportionality. And so I'm just going to cross multiply here so that I'm going to have xy and xa together. And that's going to be equal to xz times xb. And that's what we were trying to prove. So we have shown that if we start out with a triangle that it has an acute angle here, and the non-designated angles here have altitudes drawn in, then we can show that this is going to hold, that we have this product that shows up. Now let's talk about what happens when we change the acute idea. It wasn't until after I had done this proof that I realized how critical it was that we designated that this angle was acute. Let's think about this. If we had let this triangle XYZ be a right triangle with X being the right angle, look at the implication here. That means that X here is already 90 degrees. But we want these two angles to be 90 degrees because we're drawing this altitude in. In that case, this triangle will not exist in the plane. So this is no longer something for plane geometry. So you could draw this in, say, a spherical geometry where you have two 90-degree angles here, but this isn't going to work in the plane, and so this fails. We can't have a proof in plane geometry where x is 90 degrees, and so this proof would fail at that point. And you could provide your counterexample here. You would demonstrate right here that there is a contradiction here. The last option is we can change this to obtuse. Now, I'm going to have to redraw my diagram a little bit. We're going to open this up a little bit as if x were a hinge and make this into an obtuse triangle. And at that point, what happens is the altitudes cease to be on the inside of the triangle and they flip to the outside of the triangle. That's one of those weird things when you're learning about finding the area of a triangle. Sometimes the height of the triangle has to be measured from the outside of the triangle. And I think this is probably an oddity about triangles that may be confusing to students about finding the height of your triangle, but most of the time you're measuring inside the objects, and then all of a sudden you get a few of these obtuse triangles and you're measuring on the outside to try to find the height. Well, that's exactly what happens here. As you designate that x has to be obtuse, your altitudes move to the outside of the triangle, and so you no longer have this type of situation where you have a point of concurrence inside the triangle. And again, you're not going to get an argument like this. You don't have an intersection point on these opposite sides here because the altitude's on the outside of the triangle, so there's never that intersection of this altitude interior to the triangle, and so this doesn't work. This particular proof critically relies on x here being acute. If it's 90 degrees, those altitudes kind of push out and kind of become the sides of the triangle. And if it's obtuse, those altitudes go further out and they're outside the triangle, and so you don't get these little segments at all. Hopefully you found this interesting. Cheerful calculations.